Welcome to another Explainer. Today, we're diving into something absolutely mind-blowing. Have you ever wondered how incredibly dense theoretical engineering math, the kind of complex equations that completely cover chalkboards in university lecture halls, actually translates into real, life-saving technology? Well, we are going to explore exactly that. We're taking a journey from the abstract world of mobile robot kinematics straight into the operating room, where these mathematical principles are powering advanced surgical robots to literally save lives. It's an incredible story of engineering meeting biology. To set the stage, we kind of have to look back at a famous piece of science fiction that set the philosophical standard for everything we're about to discuss today. This is actually from a fictional handbook of robotics, supposedly dated 2058 AD, quoted in Isaac Asimov's I, Robot. It simply states, "A robot may not injure a human being, or, through inaction, allow a human being to come to harm." It's a massive, high-stakes directive. The ultimate purpose of a robot, before absolutely anything else, is to protect human life. But how do we actually program a machine to guarantee that? Okay, let's dive into this. Here's exactly how we're going to break it all down. Number 1, the rules of robotics. 2, degrees of freedom explained. 3, mapping robot movement. 4, theory meets surgery. 5, the Da Vinci masterpiece. And 6, the future of precision. We're moving from dense engineering theories straight into an incredible medical application. So let's get started. Section 1, the rules of robotics. So Asimov's laws, they sound absolutely great on paper, right? A robot shouldn't harm a human, it should obey us, it should protect itself. But here's the reality. A machine doesn't understand philosophy. It only understands data, coordinates, and physics. To guarantee that a multi-million-dollar piece of heavy machinery operates safely right next to fragile human bodies, engineers have to use incredibly complex kinematic mathematics. They literally have to know exactly where the robot is, how fast it's moving, and exactly where it's going to be a fraction of a second from now. Section 2, degrees of freedom explained. Now, if you're a gamer or you've ever flown a drone, you probably understand this intuitively. But mechanically speaking, a degree of freedom, or DOF, is the absolute minimum number of coordinates needed to completely specify how a mechanical system can move. In our three-dimensional world, there are 6 total DOFs. You've got 3 translational degrees, moving along the X, Y, or Z axes, which is basically forward-backward, left-right, and up-down. And then you have 3 rotational degrees, roll, pitch, and yaw. These 6 coordinates determine every single possible way a machine can act in space. And this brilliantly illustrates the concept. Think about a basic mobile robot, or even just your everyday car. A car really only has 2 controllable degrees of freedom. It can go forward and backward, and it can rotate its steering angle. Because it completely lacks a sideways translational degree of freedom, you can't just magically slide your car directly horizontally into a parallel parking spot. Instead, you have to perform this complex, continuous trajectory, usually while sweating and hoping nobody is watching you just to park the thing. Which brings us to a major concept in kinematics, the holonomic system. Basically, this is a system where the controllable DOFs are exactly equivalent to the total DOFs available in that space. Like we just talked about, a car is non-holonomic. Its controllable DOFs are less than the total DOFs, which is exactly why parking is so annoying. But if you can build a holonomic robot, or even a redundant one where the controllable DOFs are greater than the total DOFs, well, you've just unlocked an engineering superpower. That robot can instantly move in any direction, at any angle, at any given time. Section 3, mapping robot movement. Now, mobile robots move totally unbounded with respect to their environment. They don't have a fixed track telling them where they are. So, to figure it out, engineers map a specific point on the robot's chassis against a global reference frame. Using intense trigonometry, specifically orthogonal rotation matrices, they are constantly converting the robot's local velocity into a global position. It takes massive computing power just to know where a robot is sitting in a room. Okay, so the crucial point here is understanding the clear difference between forward and inverse kinematics. Forward kinematics is when you know the robot's wheel velocities and you use that data to estimate where it's going to end up. It's basically asking, if I push the gas exactly this hard, where will I go? But inverse kinematics is the exact opposite. It asks, if I need the robot's arm to be at this exact microscopic coordinate in space, exactly how much velocity and rotation do I need to apply to every single joint to get it there? Motion planning using inverse kinematics is incredibly difficult to compute, but it's absolutely crucial for high-stakes precision tasks. Section 4, theory meets surgery. All right, let's bring this all together. Think about a human surgeon. Surgeons are absolutely brilliant.
but their hands are biologically limited. Human hands have natural tremors. Our wrists just can't fully rotate 360 degrees. Our fingers are way too large to perform microscopic suturing without opening a patient wide up. But what if we took the math of inverse kinematics and holonomic systems and actually built a machine that totally bypasses all of those biological flaws?
Section 5. The Da Vinci Masterpiece. 7. This is kind of a magic number in robotics. The surgical arms of the Da Vinci system possess exactly 7 degrees of freedom. Remember our earlier point? A 3D space only has 6 total degrees of freedom. By integrating 7 DOFs, this system is highly redundant. It literally exceeds the mechanical capabilities of the human hand, allowing it to maneuver in ways that flesh and bones simply cannot. And they achieve this through what is called endo-wrist technology. We're talking about highly specialized instruments with wristed tips that mimic a human wrist, but are honestly far better. Because they utilize complex rotational, pitch, yaw, roll, and multiple axes of translation, surgeons can perform highly complex dissections and suturing in incredibly tight spaces inside the human body. They can literally maneuver around organs and tissues with total freedom, never feeling restricted by the angle of their own arms. Now, what's really interesting about this is that kinematic precision is totally useless if you can't see what you're doing. Notice the 10x multiplier here. The Da Vinci system integrates a high-definition 3D vision system that magnifies the surgical field up to 10 times. It pairs crystal-clear visual clarity seamlessly with the surgical arms. So when the surgeon looks into the console, they have a flawless, magnified understanding of the spatial depth between the instruments and the patient's anatomy. So all of this culminates in what's known as console-to-patient movement translation. The surgeon sits at an ergonomic console, moving their hands intuitively. The system uses inverse kinematics to translate those human movements into the local reference frame of the robot perfectly. But it does 2 amazing things in the process. It scales the motion, turning a large hand movement by the surgeon into a tiny microscopic action inside the patient. And it applies tremor filtration, completely eliminating natural human hand shaking. Because of this, the surgical arms can enter the body through tiny ports just 5 to 8 millimeters wide and access multiple quadrants of the body without ever needing to reposition the patient. And as you can see, this table perfectly summarizes the real-world impact. All of this complex math directly transforms the patient experience. By mastering inverse kinematics and achieving 7 degrees of freedom, we transition from open surgery to minimally invasive surgery. Patients experience massively reduced postoperative pain, far fewer complications, and much faster recovery times. This isn't just cool technology, folks. It's a literal revolution in human health outcomes. Section 6. The future of precision. So we're bringing the narrative full circle back to our beginning. Isaac Asimov's first law stated that a robot must not injure a human being or allow a human to come to harm. Through continuous advancements in continuous trajectory planning and multi-site surgical robotics, the Da Vinci system is the ultimate real-world embodiment of this sci-fi law. We've used math to literally program these machines to become the ultimate tools for preventing harm, curing disease, and healing humans. Which leaves us with this final thought. As robotic systems continue to master even more degrees of freedom, shrinking down further, and perhaps integrating even more advanced spatial mapping, what new medical frontiers will these machines allow us to conquer next? Could we eventually perform cellular-level surgeries? The possibilities at the intersection of kinematics and medicine are truly endless. Thank you so much for joining me on this explainer, and I absolutely can't wait to dive into our next topic with you.